Our next presenters, an FTC team from Virginia who won the Inspire Award at the Shenandoah Caverns Qualifier, is Capital Bots.
Hi, we're Team Capital Bots 14575. My name is Amini, and we're so excited and grateful to be presenting today. Our team consists of 9 kids, and we are based in McLean, Virginia, near Washington, D.C. This is our 3rd season, and it was definitely one of our most successful. We won Inspire, Connect, and qualified for Worlds. We'll be talking about our organization, outreach, and robot design throughout this season. Team organization and planning was crucial, especially for this year. We had in-person and virtual meetings and decided to utilize preseason to really focus on outreach. We also planned the prototyping and integration of subsystems on our robot. We made use of the engineering process and modified it to work especially for our team. This definitely improved our robot design and efficiency throughout the season. This is our team ecosystem where we collaborated with FLL, FTC, and FRC teams for virtual events, showcases, as well as parts and field elements. We used this opportunity to connect with even more teams, and we look forward to continuing those relationships in the following seasons.
We connected with multiple professionals. We connected with a computer vision engineer, a robotics engineer who taught us about autonomous algorithms, a program manager who taught us about automation, a FIRST alumni, and an IP lawyer who taught us how to patent one of our robotic innovations this year. We also conducted multiple virtual events. Earlier in the season, we hosted an online free intro to FTC workshop and a CAD workshop in partnership with Almond Robotics. We also presented at Wolf Corp's Skystone showcase last year, and we conducted our own robotics showcase later in the season, both in person and online, and partnered with an FLL team to promote FIRST as a whole. We also made great fundraising efforts this past season. Our own team members conducted and taught a CAD, Java, and Arduino course, all very successful. We also received donations from many companies, leading our total fundraised amount to reach about $8,000. Here are some testimonials and work samples from our courses. We are also conducting more online CAD and 3D printing, Java, and Arduino courses during the summer. So there's more information about that on our website, capitalbots.org. Transitioning to our robot, we created a pasta roller intake design for a quick intake of rings onto our conveyor belt. Here are some images and GIFs of our intake as a whole. Some of our intake innovations are the custom rollers. We 3D printed to help bring in rings more efficiently. All of our intake was powered by a complex gearbox we designed. We also attached heat shrink nails to our conveyor belt to create a more secure and fast ring carrying system. This is the innovation we are currently trying to patent.
Hi, my name is Neil. I'm going to go talk further about the robot. So now we're going to talk about our launcher mechanism for this year. Before assembling the original launcher, we designed everything in Fusion 360. On the right are our custom designed and 3D printed mounts that we use to attach the launcher to our robot. On the left is the trigonometric equation, which we use to estimate our approximate launching angle that we would need. So this is our design of our launcher trials. On the left, on our first design, had motors protruding from the bottom, causing the collection box for the rings to sit too high for the conveyor belt to deliver it. By flipping the launcher 180 degrees with the motors pointing up, we were able to keep the ring collection at a lower height, allowing for easier belt to collection box integration. We had several challenges while trying to 3D print a collection box such as FDM printing complications like warping and poor bed adhesion on larger prints. Because of this, we decided to fabricate a reliable hardboard collection box instead. So this is our wobble goal mechanism. We designed an arm that is long enough to reach the top of the wobble goal when mounted to the robot to ensure there wouldn't be any issues when dropping the wobble goal. The arm is mounted on a channel and the motor is mounted inside using miter gears. This year, we wanted to improve the accuracy of our robots' movements, so we worked on utilizing a gyroscope to aid our movement. Before we begin, it is important to note that we had two navigational systems that we used, so we decided to code them separately. To do this, we used GitHub to keep our code organized in branches. Initially, when attempting to have our robot move straight, we noticed that it would veer towards the left or right. Use the inertial measurement unit, the gyroscope within the hub, to counter this. The IMU reports the direction and angle of the report, and if the robot is moving too far to the left or right, we were able to adjust the powers in the motors in the drivetrain to straighten its path. We also used this feature to create very accurate turns. One of our main goals this year was to implement accurate path following with odometry wheels in Roadrunner. After assembling the Open Odometry version 1 modules by FTC team 18219 primitive data, we started to work on implementing Roadrunner, a motion planning library by Acme Robotics. The library is designed primarily for autonomous robotic movement and allows for complex path following and generation while maintaining control of velocity and acceleration. This allows robots to have more accurate and advanced path following capabilities. The library allows for two different control methods, velocity PID and feed forward. We used feed forward control as we were using odometer wheels, which we chose to use because odometer wheels could record any extra motion that may or may not have been caught by the drive encoders, such as wheel slippage and collisions with other robots. We managed to successfully implement Roadrunner in both our autonomous and teleop, allowing for power shot, driver automation, and an accurate autonomous. We'll now talk about CV and what we did to implement it. By using an external camera, we detected the number of rings at the start of the autonomous period by using the default FTC TensorFlow Lite model and used this to dictate where the wobble goal would be dropped depending on the number of rings in the stack. To save time, we turned the camera on and we would have it continually detect the stack during the initialization period. This way, we didn't have to waste a few seconds when we started the match.
Thank you to Capital Bots for the highly comprehensive presentation. Their team structure and plan for the season was very detailed and organized.